start the recording. And I believe my desktop audio is recording because I checked it beforehand. Yes, it is. All right. So, let's just go ahead and get going because probably just be us. So we talked about capacitance and like potential and all that stuff. The last session, you guys had your quiz on it yesterday. So just a refresher, what is a capacitor?
Oh God. Already forgot the Hey, Nabbit, forgot the definition already.
Well,
The ability to store, I believe, right?
that is capacitance. And the ability to store what?
Well, the ability to store energy, honestly.
Um,
So,
More specifically,
so capacitance is the ability to store it. So, the capacitor should be the ability to use them, I believe. It's to be able to use that energy.
more specifically, what kind of energy is it storing?
Oh, potential energy.
And how is it storing potential energy?
Uh, how? Oh, it's by the two plates,
Mm-hmm. And what do the plates have?
a positive and negative charge.
Charge. That's what I was going for.
Okay, then.
The capacitor stores charge, and with that charge, it generates an electric field and stores a potential energy. So, what is a capacitor? Or specifically, what kind of capacitors have you been seeing in this class?
The para plate capacitor.
Exactly. So, what is a parallel plate capacitor?
Uh,
Describe it
let's
to
see.
me. What does it look like?
Well, two plates that looks like a sandwich in a way, just without anything in the middle.
Yep. And would you say the plates are parallel to one another, or are they perpendicular?
Parallel, because I mean,
Yeah.
like I said, a sandwich.
Yep.
So it had to be
It's a
a
Klondike.
perpendicular sandwich. I would
It's
love to actually see that.
it's like a Klondike bar. So we have these two parallel plates, and you mentioned something about how they store charge.
Yes.
How do they, like, in what way?
The charge is stored in the plates.
So what, like, both plates have the same, like, charge on either side?
Yes, just one's positive, the other one is negative.
Exactly. One's positive, one's negative. So one side is going to be positive, one side is going to be negative.
And I believe that's indicate if you had to look through that graph, I believe it's indicated as the positive is the bigger line and the negative is the smaller line or something like that.
What do you mean by that?
It's some of the graphs that the professor was showing us.
Oh, where you have, like, a larger line and a smaller line?
Yeah, stuff like that for voltage.
That
Or
would
like
that usually indicates a battery, not a capacitor.
okay.
So, if we go ahead and hook up this capacitor to a battery, let's say something like this, and we have our battery, which side is going to be which for the capacitor? Which side is positive, which side is negative?
I believe the top. Wait, no. The battery is on the top is positive, and the battery on the bottom will be negative. So,
Wait, what?
I was talking about the battery.
But
Yeah.
top and bottom, but it's the battery's from left to right.
Okay, so
I'm
well,
heading
I
left,
mean,
left side, right side.
okay, left. All right, sorry, I was looking like completely opposite way. The left is positive, the right would be negative.
For the battery. So what does that mean for the capacitor?
That means the left of the capacitor should be gaining the positive charge. So shouldn't it be positive?
Yep.
All right, so that means that okay, that's all right.
And that would mean the right side is also positive. No, it's negative.
Getting the negative side. Don't confuse me now. I'm like,
Yeah.
wait, what?
So basically, the way you can think of it is if you go in a loop, if you were to like, for example, straighten this all out into a straight line and go around, the capacitor is going to be opposite of the battery because we gain 12 volts. For example, if it's a 12-volt battery, we'll gain 12 volts going from negative to positive across the battery, and then we lose 12 volts going from positive to negative across the capacitor.
Ah, okay.
And then just quick refresher, how is this voltage across the capacitor and the charge related to the capacitance?
Oh, the formula C is equal to charge over the voltage.
Exactly. C is equal to Q over V. Boom. That's pretty much everything you need to know in terms of what the capacitors actually are. And now you just need to work on working with capacitors in actual circuits and in series and in parallel and all that other crap. And
To
it
be
just
honest, if the quiz was just only about that capacitors, I feel like I would have aced that quiz. But I only missed one question on that quiz, so that's the
mhm.
only good thing.
Welcome, Michelle. We just talked about the capacitors and just in general, like which side is positive, which side is negative, and yada yada yada.
Okay.
Do you have any questions about that at all?
I don't think so.
All right. Well, in that case, let's just go ahead and hop into some examples. And my idea for this session is, honestly, this little example thing I've prepped here is probably going to take us maybe 25, 30 minutes to get through, and that's if we move slowly. Honestly, we could bulldoze through this in 10, 15 minutes, and my idea is that is ideal. And then I'm thinking you guys can pull up some example problems from Flip It or from the class questions or whatnot that you had troubles with potentially, and we could work through those as well because I know some of the Flip It stuff can get a bit annoying. There's one problem in particular I know you guys will probably bring up that students in the past have brought up.
Okay. Well, I haven't started on the flip it yet, to be honest. I've
Oh,
started on the other stuff, get those out of the way, but I haven't started on the homework yet. I was planning to do that right after this.
mm-hmm. Wait, wouldn't it be the homework for the material that you have your quiz on tomorrow? Wouldn't that have been due on Thursday?
Uh,
Or
no.
oh no, the homework is oh wait, I'm getting things mixed up. So your Unit 12 homework is due tonight, and then your quiz is tomorrow.
It's due. It is due. The homework is due tomorrow at 11 a.m.
Okay.
But essentially, yes.
Okay. Yeah, sorry. For some reason, I got that mixed up. It was like you do your homework for the next class, and then you go over the stuff in class. Whatever. Let's just go ahead and hop into this example. So we're just going to go ahead and have a capacitor, capacitance C1. We're going to hook it up to a battery with voltage V0. Sort of like this. Let me actually go ahead and just draw it smaller because we're going to have a bunch of these drawings. So we're going to have C1.
It's an icky day out there. It's raining again.
I wouldn't know. I haven't gone outside in 3 days.
Well, you know what? Well, I can hear it, so.
Actually, it isn't raining where I am. I'm right downtown Baltimore.
I'm at Laurel, so.
Yeah, you're about 20 minutes out. So we're going to have our capacitor hooked up to our battery, C1 and V0. So we want to know is how is the charge on C1, which you guys should know how to calculate, how is that charge going to change if a second capacitor, C2, is placed in series with C1? So we're going to go ahead and hook up a second capacitor here C2 in series with C1? Take a minute to think about it. Would the charge increase or decrease or stay the same? Do either of you know? Would it increase, decrease, or stay the same?
I'm still trying to figure it out. I know the voltage would be different.
Exactly. What would happen to the voltage?
I believe it will decrease by. I believe it will decrease.
Why is that?
Because now it has to go through two capacitors,
Mm-hmm.
and I believe depending on depending on what the battery is, the numbers and all that, it will always since there's two, it would decrease by a factor of two.
Well, not necessarily a factor of 2. Like, if the capacitances were equal, then it would be a factor of 2.
Oh, okay, so assuming that they're not, assuming this is not equal, but
Michelle, did you want to add something?
Oh, I was just gonna say the charges stay the same.
Why is that?
Because it's equivalent to like um, one capacitator.
Mm-hmm. We're talking about just the charge specifically on C1 itself.
Oh, think is it cause I'm not sure.
How do we relate? So Roger mentioned that the voltage is going to go down because they're connected in series with one another. So how do we relate the charge to the voltage?
oh, so wait, capacitor is equals to the charge over the voltage. So in this case, the voltage would equal the charge over the capacitance.
Mm-hmm. So we know voltage is going down, and we don't know what's happening with the charge. That's what we want to find out. Is the capacitance changing?
I want to say no.
No, it's still the same good old C1. We're not shoving a dielectric in there. We're not pulling the plates further apart. We're not shrinking the capacitor plate size. Capacitance is staying the same.
So if voltage is decreasing and that's staying the same, the charge needs to. I believe the charge needs to increase in order to keep it the same.
Not quite.
Oh, so it's the opposite. So it will also decrease.
If the denominator decreases, the numerator also has to decrease for it to stay the same.
Okay,
like if you have 3/6 and it decreases to 2/4, for example. So yeah, because the voltage goes down for C1, the charge on C1 has to go down, and the voltage went down because they're connected in series.
Okay then.
And so, do you know how would we actually calculate this new charge on C1?
This has to do with C1 plus C2 is equal to C12 stuff, right?
Potentially.
Well, the only thing we know is the voltage would decrease.
Mm-hmm. Do we have a way of figuring out how much voltage would decrease? At least in terms of C1 and C2?
See, we know the capacitors has to stay the same, so we got that. And then with the voltages, crap, what's that? I need to grab my formula sheet one more time because I need to see that.
You don't need a permit or nothing.
So do we do 1 over C is equal to 1 over C1 plus 1 over C2, and then we just multiply that value by the voltage?
So you mentioned the 1 over C12 is equal to 1 over C1 plus 1 over C2. That's right. That's a good starting point. And then what did you say?
I said multiply by the voltage to get the charge.
Multiply by the voltage? By what voltage? Just multiply by V naught?
Yeah, V naught.
That would give us the total charge for the entire net capacitor C12. What
Okay,
if we...
then would I just do this with just C1 then?
I think I would think about, I mean, first of all, I'm going to go ahead and do this. Another way, an equivalent way to writing this, 1 over C1 and 2 is equal to 1 over C1 plus 1 over C2. Another way you can write it is C12 is equal to C1 times C2 over C1 plus C2. I just think that's a neater way to put it. And then what I would think about is potentially writing some sort of a ratio of C1 to the total capacitance C12.
Okay.
So where would we go from there?
So you would just do C1 C1 over V is equal to C2 over V.
So
Is
you're
that right?
C1 over V. Does C1 over V have any useful, or would it be C1 times V?
Yeah, I think C1 times V, actually.
Mm-hmm.
C1 times V is equal to C2 times V. Right?
Not quite. It would be.
Oh.
It'd be C1. I mean, here. Let me actually pull up your formula sheet because there's some useful stuff here.
Oh, okay. I think I got it. It's we're looking for C1, right?
Yeah.
So it'd be C1 is equal to C2 times V2 over V1.
So it was. Wait, sorry. Repeat that. With.
C1 is equal to C2 times V2 over V1.
Are the charges on C1 and C2 the same?
They are the same, I think.
They are the same but opposite charge. It's the opposite. The one's positive, the other one's going to be a negative, I believe.
That's for the two individual plates on a single capacitor. Are the charges on C1 and C2 equivalent here? Wow, he actually doesn't. Does he not give the cheat sheet anymore? Damn, he doesn't. Oh, that makes things a lot more complicated. I was relying on something that I thought was on the formula sheet. It was on the formula sheet in the past.
Well, time for you to show us on that one then. Huh.
So,
well, C2 will have its own different. It would be a different charge on C2 because C1 and C2 will, I believe, will have different charges.
So, they do actually have the same charge. So,
okay then.
Two or more capacitors, if they're all in series, they'll all store the same amount of charge on them. So, what Michelle was saying was actually right, and I got it mixed up in my brain. So you have C1 V1 is equal to C2 V2, which we then would also know is equal to C12 V0. Right? No, it wouldn't. Sorry, I'm getting things mixed up. But the main idea here is that we know that the charge stored on C1 when we connect C2 is going to decrease because the voltage across C1 is going to decrease. And that's the main idea. I'm now realizing this question is poorly worded, and I also need to restudy my capacitor knowledge.
Oh boy.
But you guys pretty much understand. You pretty much understood the concept, and honestly, most of your quiz tomorrow is just going to be simplifying circuits down, or like comparing charges or voltages between two individual capacitors within a circuit. It'll be
basically concepts.
Yeah, it'll be similar to what you've seen on Flip It. So let's not worry about actually calculating values here. Let's just worry about going through and doing the concepts for each of these. Is the charge or the voltage or whatever we're worrying about, is it going to increase, decrease, stay the same, yada yada.
Okay.
So how would the charge on C1 change if C2 was, instead of being placed in series, was placed parallel? So we're going to have, oh god, that's bad. Alright, so we're going to have C1 and then C2 and the battery. Is the charge on C1 going to increase, decrease, or stay the same compared to before C2 was connected?
Okay, let's see. The capacitance is still, again, will stay the same. And I believe the voltage also decreased, so when did the charge also decrease?
Why does the voltage decrease?
Oh, wait a second. Actually,
Does it decrease at all?
that's the one thing I'm trying to figure out.
Does the voltage perhaps increase? Or does it not do anything at all?
The voltage stays the same, right?
Why is that?
Cause Because the Q and the I'm not sure if the capacitance and the charge, like, I'm not sure if they're both increasing or both decreasing at the same time.
Well, we're talking about just individually C1 here. We have
C1.
so for example, this is C1 and this is C2. Essentially, C2. Essentially, we're going from this completely disconnected, not connected to the circuit, and then boom, we connect it. What happens to the charge on C1?
Like after connecting it?
Yes.
Would it decrease?
Why?
Because a charge is leaving the plate and going to the one parallel to it.
Now that would make conceptual sense, would it? That does. I think that makes conceptual sense. It makes sense. You connect another plate, and the charge leaves the one and goes to the other. What class are we taking? Physics 122. Does anything in this class make conceptual sense?
No.
No, it does not. So what's actually happening here is anything, and honestly, this is sort of, I dislike how he covers capacitors first and then goes to other circuit stuff, because you guys haven't covered Kirchhoff's laws, but Kirchhoff's loop law states that any loop around a circuit has a total voltage of 0. So, for example, we gain voltage across the battery, we lose it across this capacitor, and we come back to the start. Or we can do this loop here. So essentially, the voltage across the two capacitors is the exact same, and it's still that exact same value as before we actually connected the second capacitor.
Okay, then.
So the voltage doesn't change, and the capacitance of C1 hasn't changed. So, therefore, the charge has to stay the same. It doesn't really make sense. We connect another capacitor. Why doesn't the charge on the first one change? That's physics for you. So now, what would happen to the charge on C1 if C2 was placed in series with C1, so this first example here, and a dielectric was placed between C1's plates?
Oh boy.
So we know from before without the dielectric, we know the charge is going to have to go down. Right?
Okay, so... Yeah. Let's see. Yeah, the charge has to go down, and then the dielectric...
So what does a dielectric do? What happens to a capacitor when we go ahead and we place this dielectric thing? I'm going to draw it as... Oh god.
Well, if I at least remember correctly, if you put the dielectric in the middle, the stored energy definitely increases.
Why is that?
Let's see.
I was gonna say when you put a dielectric in between a capacitor, the electric field decreases.
A capacitator. Capacitor.
Yeah, capacitor.
Capacitor. What's taters, precious? So you're saying the electric field decreases?
Yes.
And why would that be?
Because the electric field normally goes from the negative plate to the positive plate, and then when you add a dielectric, there's an opposite electric field going from the positive to the negative plate.
Okay. So, if the electric field decreases, theoretically, what would happen with the energy? The energy would have to decrease if the electric field decreases. But didn't Roger just say that the energy increases?
Yeah, the energy should definitely increase. I do remember that rule for capacitor, for
So-
the dielectric.
One of you's wrong. Which one of you isn't? I guess more.
Which part is I don't know.
So, Roger, explain why does the energy increase? Try to give your interpretation.
The only reason I believe that it does increase because of what he said in class. I'm just trying to remember everything on that. Okay. Let's see. I'm literally trying to pull up the notes.
So, if we put a dielectric between capacitor's plates, and most dielectric you'll see have a dielectric constant greater than 1. So, like, for example, water has a dielectric constant of like 75 or 80 or 100 or somewhere around there. What happens to the capacitance when we place the dielectric?
Okay, I do believe the capacitance should increase.
Mm-hmm. The capacitance increases, so what happens to the energy stored?
Oh, okay. Since the capacitors increase, the stored energy should increase.
Mm-hmm. Exactly. The stored energy increases when the capacitance increases because half CV squared here.
Okay.
So, would we be able to know anything about the charge? If we place a dielectric between capacitor plates, does the charge increase or decrease?
What was this again in series?
Let's just ignore let's ignore C2 for now. Let's just think about C1. We place the dielectric.
Oh, if it's just that, it should increase.
It should increase, right? But then by connecting C2, the charge decreases. So we actually don't have a way of knowing whether it's greater or less than. We'd actually have to calculate and use actual values for the dielectric and the capacitances. So it's sort of a bad trick question. And I'm a bad SI pass leader for reusing this question even though I knew this was bad. So, but you're right. Connecting the dielectric causes the charge to increase, which then, and then the series would cause it to decrease. And then parallel makes it stay the same. So, what happens to the charge in C1 if a slab of conducting metal is placed between C1's plates? So the conducting slab is going to cover half the distance between C1 and C2. sorry, half the distance between C1's plates. So something like this. Is our charge going to increase or decrease?
Metal conductor slab. Hmm.
Would the capacitance increase?
Capacitance increases. Why?
Because the distance between the
Yeah.
two decreases.
Exactly. Distance decreases. Capacitance, epsilon naught A over D. D goes down, C goes up. So what happens to the charge?
Should increase.
Increase. Exactly. Capacitance goes up, charge needs to go up as well. So what happens if the battery is disconnected and then the distance between the plates is halved? What's going to happen to the charge? The battery's disconnected, then the distance is halved.
This is half as in like it gets closer to each other?
Yes.
Okay, the charge. Let's see. The voltage should definitely decrease. The capacitance should stay the same, I believe. Wait, no. No, because since the distance decreasing, the capacitance has to increase. So the charge has to increase.
But we're disconnected from the battery. If we're disconnected from the battery, wouldn't that mean that the charge has nowhere to go? So the charge...
Okay, the charge has to stay the same.
Exactly.
But I do believe the voltage does change.
Yes, exactly. The voltage changes.
Okay, yeah, you're right. The charge stays the same. Yes, the only thing that does change is the voltage, which yes, the capacitance does change.
Yeah, exactly. So distance lowers, so that means the capacitance increases. The voltage would also then increase because the charge doesn't change because we're disconnected. So what would happen to the charge on C1 if C2 is placed in series, then the battery is disconnected, and then the distance between the plates on C2 is doubled? So connected in series, then the battery is disconnected, then the distance between the plates on C2 is doubled.
Okay, so again, since it's not connected to the battery, when the distance changes, the voltage definitely changes. So if we just focus on C1, the capacitance still stays the same. Wait. No. No, since there is change in voltage, the capacitance will change as well. So wait, wouldn't it be the same? The charge would just stay the same?
From the exact initial scenario?
Oh, so hold up. You gotta place in the series first. Okay.
Mm-hmm.
So, whew.
So let's go through this step by step. First, we
Ye-
place C2 in series. What happens to the charge on C1?
Well, the charge of C1 should equal the charge of C2.
Mm-hmm. But the initial connecting of C2 causes the charge on C1 to increase, decrease, or stay the same.
I believe the correct answer is decrease.
Decrease, exactly. Remember from the first one. So
Okay.
then we're disconnecting the battery. Does disconnecting the battery do anything about the
No.
charge? No. And then the distance between the plates on C2 is doubled. Does that do anything to the charge after the battery is disconnected?
No.
Nope, I'm fucking with you. Anything that happens after the battery is disconnected doesn't affect the charge.
Okay, so that means the only it's the charge of C1 still decreased because of, connecting in a series, but afterwards it doesn't do anything else.
Exactly.
Okay. Boy, if these are the type of questions for the quiz, oh boy.
See, you just have to think about things step by step and figure out what happens in each individual step. So now we're going to go ahead and connect C2 in parallel. And then the battery is going to be disconnected. And then a dielectric is going to be placed between C2's plates.
Oh god.
Essentially, we're connecting C2 in parallel, and then we're cutting off the battery, and then we're placing a dielectric between C2's plates.
Well, okay. So the battery does not affect the charge whatsoever. Let's see. In parallel, C1 equals C2. Before the dielectric, of course.
The capacitances are equal? Or...
The capacitance in parallel should be equal until you put in that you put the dielectric.
The capacitances aren't equal. There's something else that's equal.
The voltage is
voltage. There we go. Mm-hmm. So initially, after placing C2 in parallel, does the charge change on C1?
The voltage stays the same, and that should mean the capacitance should not be changing, I don't think. So the charge just remain the same.
Yeah, exactly. Charge stays the same for the first step. Then we're going to disconnect the battery, and
The
then
charge still remains the same.
and then we're placing a dielectric between C2's plates.
Well, C1 still stays the same with the charge, I believe. It's just C2 is the one that has the different change in charge because of the dielectric.
Are you sure about that?
Not really. I do know there is a change in C2 because of the dielectric, and I do believe the charge of C2 should be affected.
So what happens with C2? So the dielectric is placed. So what changes with C2? What increases because of the dielectric?
I believe the charge should increase. Well, okay. The store energy increases, so that means the capacitance should increase.
Yep, and therefore the charge. Does the voltage across C2 change?
No.
Nope. So that would still be the exact same voltage across C1. So, yeah, no change in charge. You were right from the start. You were skipping about 3 steps in between, and I wanted to make sure you actually understood the connection.
Okay. Well, I mean, we were still only focusing on C1, so I was like, well, I'm pretty sure that dielectric does not affect, but I wasn't sure on it, so.
Yeah, so because the battery was disconnected, the voltages up here are essentially locked in place, and they're not going to change. So now, what's going to change? How's the charge of C1 going to change if 2 capacitors are placed parallel to one another in series with C1? So let me visualize this. So initially, we have C1, and then we have our battery down here, and then we have the connection around. And then what we're doing is we're placing 2 more capacitors, C2 and C3, parallel to one another, but in series with C1. You see what I mean? So
okay.
C2 and C3 are parallel to one another, but C23, the total net capacitance, is in series to C1.
Okay.
And then a dielectric is placed between C1's plates.
Oh, God. Okay.
So do this step by step.
Well, the first thing is about C2 and C3.
Mm-hmm.
They're parallel to each other. The voltage should be the same between 2 and 3.
Yes.
So that means C2, the voltage in C23 should have the same voltage.
Mm-hmm.
Then they're in series. So C1's charge should equal C23's charge.
Yep. And is that charge greater, less, or equal to the initial charge on C1 before C23 was connected?
I think C1's is greater because in order the charge on C23 is to get that you have to add those 2 charges together.
I'm talking from the initial situation when it's just C1 in the circuit.
Oh, if it's just C1,
It's literally just a 2 capacitors in series problem, right?
yeah. So the charges should still be equal. I
So
think
is that-
I'm trying to fully understand the question. That's really is it.
I'll give you a hint. You can just treat this problem as if C2 and C3 are just a single C23 that's in series with C1.
Okay.
So how does that simplify the problem?
Well, greatly. And that's why I believe I was trying to figure that one out. It's just the initially part. It's like, was greater than or less than.
Didn't we do that exact problem right at the beginning with 2 capacitors in series?
Oh, so it's okay. So the chart. So it's basically Q1 is equal to Q23
Mm-hmm.
because of. Okay, so
And that is greater or less than the initial charge on C1 before C23.
Oh, so you're okay. The charges of Q2 and Q3, basic. Okay, I believe it's supposed to be greater. I believe Q1 is supposed to be greater than Q2, but Q2 and Q3 are equal to each other. Something like that. I know what type of question you're trying to ask. I'm still trying to understand myself, trying to figure it out.
We did this exact same thing for the very first problem. When we have a new capacitor introduced that's in series with the original one, the voltage across the original capacitor has to decrease because a second capacitor is in series. So that means the charge has to decrease. And then you just place
Okay.
and then you place a dielectric between C1's plates.
Well, the dielectric should make the charge bigger.
Yep, exactly. So once again, it first decreases from the initial part, and then it increases from the second part. It's literally just question C all over again. I'm fucking with you all over again. It's literally just question C, except instead of C2, it's C23.
Okay.
And you would have to calculate the actual values to know whether it actually increases or decreases. I love these questions. They're so fun.
Conceptually, I see why. But honestly, numbers will make it so much better.
Yeah, but then numbers mean you have to, like, take time to actually calculate things, and it's like, eh. And plus, also you have to, like,
most of the problems I keep getting wrong on the quiz are conceptuals rather than the number ones, so...
So you should be willing, you should be loving these things. You're like, we're actually practicing what you're struggling on. So we got time for, if you guys have like one question from Flip It or class questions, if you want to go over it, or discussion, like a specific circuit, capacitor circuit question that we could break down. You guys have anything that you struggled with?
I guess the ones that we could definitely go over on this would be for Flip It, the physical capacitors, and I believe this is when the dielectric is only halfway in.
Can you put a picture of it in the session text for me?
Sure. 1 second.
Mm-hmm.
Then session text. Should be this one.
All right. So, an air gap parallel plate capacitor, capacitance 20 nanofarads connected to battery, voltage 12 volts. While the capacitor remains connected to the battery, we insert a dielectric into the gap of the capacitor, filling 1/2 of the volume as shown. What is Q final, the charge on the capacitor in the final situation? So, first thing, in order to solve this problem, what's the first thing we need to know?
Okay, let's see.
What is the dielectric going to do to the capacitance?
Increases.
Mm-hmm. And how so?
Because the stored energy increases.
Okay, and by how much is the capacitance going to increase? What
How much?
What if the dielectric was all the way in, filling the entire volume?
If it was all the way in.
What would the new capacitance be?
Well, okay. I believe the capacitance should be about 4 times as much. I'm trying to remember. The capacitance definitely increases because the potential increases. The voltage stays the same.
Mm-hmm.
So let's see.
It's in your formula sheet, and it's a lot simpler than you think.
Yeah, that's what I'm trying to figure out about the formula sheet. Let's see.
If we stick a dielectric constant kappa, it's a kappa, not a K, by the way. If we stick a dielectric constant kappa into a capacitor so it fully covers it, what is the new capacitance?
So okay, so that's the unit 12.1. C new is equal to kappa CO. So
Exactly.
that's the no.
Exactly. So if this dielectric was placed all the way in, it would, multiply the capacitance by kappa, which would be 2.6. So instead, we're only sticking it halfway in.
So it would just be half the kappa.
Exactly.
What was that constant K? Because that's not on the formula sheet. Kappa. Sorry.
The constant kappa. It's a constant based on the dielectric itself. So, for example, you can just search dielectric constant of water. It's about 80. For glycerin, it's like 42.5. For benzene, it's 2.28.
Oh, okay. So
Yeah.
it's that type of constant. All right.
Yeah, it's based on the material.
So let's see. Oh, okay. But in this case, the kappa is given to us. Okay.
Yep.
2.6. So that means half that should be 1.3.
Yep, exactly. So the capacitance increases. It increases by 1.3 times. So what does that mean about the charge?
The charge.
Is the voltage changing?
It the charge should increase, but only on that half.
But we're just
But the
talking
charge
about.
will also be affected on the other half.
We're just worried about the total net charge.
Oh, so is this where we're going to have to use that electric field one? Or
How do we relate charge, capacitance, and voltage?
oh, capacitance equals to charge over voltage.
Is voltage changing?
No.
Is charge increasing? Yes. By how much?
Double?
1.3.
It's either double or half.
1.3. Remember, it's half the
1.3?
dielectric
Oh, okay,
constant.
by K. So yeah, 1.3.
So that means the charge would have to increase 1.3. 1.3 times. So essentially, but then we just have to calculate the initial charge and multiply it by 1.3.
Oh, so we still have to figure
Magic,
okay.
isn't it?
Okay, so we just need to figure. All right, so once we got.
You're just getting a bit too. You're overthinking every single one of these problems. Essentially, you're thinking about the electric field and using all these different equations down here when it's literally just staring you in the face with just those two basic initial equations.
Okay, so we just use that and then the charge since the voltage. Okay.
Oh crap! I did not hear what you just said because my headset just died. Give me a moment. This is awkward. Okay. Some video output device. We're going to those speakers, and then properties.
Oh god, there's a...
I can hear you again.
Okay, I was just going to say, I understand.
Yep. All right. Cool. I need to charge my headset before my next session in 15 minutes. Hopefully 15 minutes of charging is going to get it through the session. But that's pretty much it. Thanks, guys, for coming. I'm actually glad the headset died here at the end instead of halfway through, because that would have been real fucky. I should have charged it last night. But thanks, guys, for coming. Hopefully this helped out a little bit with the whole conceptual ideas behind capacitors and all that stuff that's going on. Good luck studying for the quiz tomorrow. Good luck getting the flip it work done tonight, Roger. You lazy procrastinating.
Hey, I got the other pre-lectures and stuff done yesterday, so I was like, all right, time to have some fun.
All right. Good man.
Thank you.
Yep. Thanks, guys, for coming.
Thank you. See ya.
See ya.